of all, I guess I'm overdressed for the occasion. I wasn't hoping for this kind of, nice setting. I should have traveled in my Polar. And we have time is short, so I'll just get to business. And just very briefly, all of you are chemists and physicists or AI. How many of you are organic chemists? Okay, fine. So you have to suffer through some of the, synthesis part, but then we are going to be talking about a little bit of, AI in material science and robotics. And the first part of the talk is actually, I have some strong sentiments in this area where AI does not work. And we'll have a discussion later. And I'll be very glad to take your questions, why I think it doesn't work and all that. But the second part is about AI actually being quite productive. So without further ado, the ongoing revolutions in chemistry, AI, What I like about this picture is obviously the robot is writing some complete mathematical nonsense there, if you look closely. So hopefully this is not what we are going to be doing. And let me introduce you to, how I got introduced to this AI and computers in chemistry. And I say we started this because, it was 25 years ago. I played bridge with people who developed Deep Blue at MIT. And, we started thinking networks and all that stuff. Nobody cared in chemistry. People thought you're completely crazy, some computers, whatever. Anyway, this is one of the oldest problems where you take a complex molecule and you try to make a synthetic route. How do I make this azithromycin here? And this has been tried for about 50 to 60 years on a computer. And my personal motivation was I went to a Nobel Prize winner whose name I'm not going to mention. And I asked him, I have this idea about using AI and computers. He looked at the watch. I was a graduate student. He said, Bartosz, you have 20 seconds. And then when the 20 seconds was up, he said, this is the most stupid idea I've ever tried, I ever heard, right? He said, look, I tried, I failed. So therefore, there's no chance you can figure this out. Okay? So that's very nice when you're a graduate student. It sort of sets you up for life. Now, the problem is this. You have molecule you wish to make and all kinds of molecules that are simpler and lead to it. This is called biosynthesis, and in the backwards direction, retrosynthesis. You see, in one step, you have about 100 options, maybe 80, something like this. In two steps, you have another, 80. So in two steps, if I expanded all the spiders, it would be 80 or 100 square. And it goes sort of exponentially like this. And the game ends when you reach two things that are shown here on pink backgrounds, meaning you can buy them, okay? So you might think that this is, I don't know, few steps, However, it does not get solved. This particular synthesis takes about 15 steps. So it's 100 to the 15th power of options, okay? And the longest organic synthesis is 103 steps. So even if you solve this problem, you would not be able to keep all the options in the memory of the computer because there would be 100 to the 103rd power, okay? So is this problem of synthesis design even solvable? And sometimes people say it's like chess. It's a one-person game, not a two-person game. But in chess, you can learn how to play in one afternoon. I'm not saying you're going to be Magnus Carlsen, but you can sort of memorize the 12 moves and then, pretend that you're doing something smart on a chessboard. In chemistry, the number of these moves is 100,000. That's why organic chemists study for many, many years to get all the knowledge, how can I make this from that, how can I change this functional group into this functional group? And maybe chess game always has some ending. Now, here in this, maybe we'll find a pathway that leads to starting materials that are buyable or not. Now, many people are now trying to do this by AI. And the idea is this. Let's go script all the databases of chemistry that we have ever seen. And I'm sure that we are going to learn all the rules and we'll be able to play. However, you see, the first example here, this you could find in the database, two molecules reacting to give you a simple drug. But the second one, very similar, you will not find because the reaction that you're actually looking for is compromised by the presence of what is called an acyl group. It's a conflicting group. So this reaction, instead of reacting similar to this to make a heterocycle, to make a ring structure, it would actually react somewhere else and you would find a soup of undesired products. Now, the problem is that this is never published in chemistry. It's in no databases, so you don't have any negative examples in chemistry. So if you're trying to do AI in chemistry without negative examples, you're sort of doomed to failure. This is an example from one of the programs from MIT, actually, where, it expands this tree, it gives you some starting molecules, but if you're a chemist, if you look at these molecules, this and this will never react like that because you would have to form an enolate at the very strained atom here. It will react from this position, not here. So why? Because it never saw a failure. When this program was trained, it never saw a failure, okay? Because it's not published. So when I say that we started this, it means that we wasted, 20 years of our lives collectively as my group in writing the rules in which there's the mechanism, there's what should happen in the reaction, but there's also, without going into too much detail, all the list of groups that are incompatible, that can lead you astray, that can make your reaction fail. And this is very interesting. This knowledge exists, but it's in the heads of good organic chemists, in textbooks, as general rules. But it's not published as reaction examples, because nobody wants to publish failed reactions. And then this particular problem, so, trying to solve it just by data, it's completely crazy for many other reasons. It overlooks quantum mechanics, it overlooks molecular mechanics, how we can cyclize molecules. It doesn't know about electron distributions and so on and so on. And once you incorporate all of these components, the computer actually can think like a chemist, but again, not just data, but this kind of dark knowledge that you have somewhere in chemistry. And if you spend 20 years, then it starts thinking, and of course there are algorithms to search these spaces. We don't want to do exhaustive searches and all that. And let me show you very briefly, just a few examples. When we tried to publish this as an algorithm, and this was 5 years ago, it was like, this is the pinnacle of organic chemistry. Then on top, if you ever think about doing something, in chemistry and sending one of these beautiful journals, they'll come back with the following question. Oh yeah, that's great, but why don't you cook it? I'm like, wow. I have an experimental lab, but we never did what is called total synthesis, this very long kind of synthesis, right? But we had no choice. So in order to convince, chemists are very traditionalist. They don't want to embrace change. So if you, I'm sorry, we're all chemists, right? But organic chemists are like, for a good reason, because they failed so many times and they say, some program, whatever. But if you spend, the synthesis like this takes at least half a year. If you spend enough time on that, and this is designed by the computer, and the blue numbers here are the most important because they're the experimental yields. So it actually worked as it should. Now, by now, you can use some of these programs that we developed. One is in ChemDraw, when you draw molecules. If you click under Cynthia is the program our group developed, the first generation of programs. And it gives me quite a kick to see papers like this in Science in 2023 from our friend Tim Cernak at Michigan, because he took a synthesis that organic chemists spent 10 to 19 steps to make this molecule. So the molecule that we are making is here, and 19 steps. And the computer said you can do it in 3. And then Tim cooked it, and it actually worked in 3. Right? So computers at some point can actually become better than chemists if you give them a chance. This is where this field stands right now. Anybody recognizes the molecule? It's the most popular drug on Earth. I was hoping for it cures cancer. No, it's Ozempic. It's Ozempic, the most popular drug is not curing some incurable disease, it's making us slimmer, right? So this is the Ozempic from Novo Nordisk, one of the largest molecules I've ever seen. And how long do you think it takes computer to plan a route that actually mimics what Novo Nordisk did? All right, there's one thing. But you have to teach the computer some logic, how to proceed in these kind of, puzzles. It's not only the dark knowledge, but a hierarchy that not all the reaction rules are equivalent. Some are more important than others. Some should be applied preferentially, and so on and so on. If you do it right, and this is a very recent paper we published, it takes 11 minutes. And this is the synthetic plan where we couldn't draw, all the molecules because it would just be able to cram it into one slide. Okay, so this is the first part. If you would like to read or use some of these programs, like I'm trying not to be a traveling salesman here. The first one, was Merck. The second one, the newest generation, Alchemy, is now part of Bruker, and there are some papers to read. But here, for me, it was like a chilling story. I really hoped about 15 years ago I can do it just based on data, code, scripting, and all that stuff. And then we went onto this bonanza of 15 years of teaching computer chemical rules, okay? So message from this part of the talk is that AI, unfortunately, in chemistry, in wet chemistry, is not an answer to all the problems we might have. If you want to play at the level of molecules that organic chemists really care, like this Ozempic. Okay, but, this thing here is about catalysis, materials, and so on and so on. And I want to show you some examples where AI actually makes infinite sense, where active learning makes infinite sense because there is no knowledge, okay? There is nothing to script. So, maybe I'll skip this. Everybody knows that? I wasn't sure what the audience is, okay? We can represent molecules as smiles, as graphs, and so on and so on. Yes? AI is about fitting, and when I talk to chemists, I say, look, we've been doing this for 100 years, everything in chemistry trying to fit it to a straight line. AI is exactly what you did for the last 100 years. It's just you're trying to fit to some kind of more complicated function, and they actually buy to it. Well, you need to know a little bit of neural networks and mathematics. I'll skip this. You need to make sure that you're fitting and not overfitting or underfitting. I'll also skip that. I'll spend maybe 1 second here. Everybody is okay with Gaussian processes, right? So and this is very powerful in chemistry. When you do an experiment, you gain knowledge. This knowledge goes back into your system, let's say maybe a robot, and the robot and AI, they work in unison and they learn, they keep learning. And of course, Gaussian process tells us where to go to minimize the uncertainty and so on and so on, okay? But you're familiar with that. So let's start. I'll show you 3 problems in which this active learning and robots were actually working together to a very, very nice end result. So in chemistry, you would like to make molecules automatically. Why? Because the bottleneck of every drug discovery campaign is synthesis of molecules. Chemists can have 300 ideas for molecules a day, but you can probably synthesize 1 molecule per month or maybe 1 molecule per 2 weeks if you're good. So if we could speed it up, and you might say, are there any precedents? Of course, peptide synthesizers. Right now you don't do peptide synthesis by hand, but you put it on a synthesizer. This is 1 Nobel Prize to Merrifield in 1984. DNA synthesizer. Without DNA synthesizer, there would be no molecular biology. This is yet another Nobel Prize in chemistry. So a friend of ours, Marty Burke at Urbana-Champaign, has been developing a robot. It looks like a 19th century steam engine or something, like, from a Back to the Future movie. But anyway, it's a collection of columns and pumps and all that to automate stitching together in an iterative fashion blocks through carbon-carbon bonds, okay? So carbon-carbon bonds are very important in chemistry, yeah? And they're not served by peptide synthesizers or DNA synthesizers. They only do CN coupling, for example, for the peptide synthesizer. So the idea is to make all of these molecules using only one type of reaction. Because automating 100,000 different protocols, it's impossible. If anybody tells you it's possible, he or she is lying. And I know at least one person who would say they can do it, but he or she is lying. So all of these robots, they do one operation, the same reaction, but to stitch different blocks, different base pairs in DNA and so on, nucleobases in DNA and so on and so on. And here, you will see in a second, Marty is stitching together these beautiful molecules of therapeutic importance using just one reaction type. This reaction type is called Suzuki reaction. So Suzuki can make double bonds. It can put two unsaturated systems together. One must have a bromide, and the other one must have a boronic acid. You stitch them together, and then at the end, you have a boronic acid that is protected, meaning masked. You take off the protection, you put another block, take off the protection, put another block, and it's like, piece by piece. However, Marty has been doing this in a suboptimal fashion, meaning every block required slightly different reaction conditions, slightly different temperature, slightly different concentration of base, and so on and so on. You cannot build a robot like this because the robot cannot optimize, 6 degrees of freedom every time you do one chemical reaction. You want to have one reaction, one conditions, okay? So the idea is the following, the challenge, to find general conditions for making these CC bonds on the robot. Now, how many dimensions we have? The reaction is catalyzed by a palladium catalyst, and there are many palladium catalysts. Which one do you take? So there's one. Ligand, it's the structure on what is on the palladium. Solvent, base, temperature, at least 5 variables. We would like to find one combination that serves all the building blocks. Okay. So this is done in peptides, this is done in DNA by now, not for the Suzuki-Miyaura coupling. So when we started doing this, we thought, okay, let's do active learning. And initially we seeded the model with some very diverse molecules to get, the basis of whatever learning we can get. So how do we choose the initial molecules? Out of the space of all the possible blocks that can be stitched together, right, like this one and this one, we chose 11. They're completely different, or, well, as diverse as possible. Then we calculated that we have roughly 530 conditions to explore. So you have 11 blocks, 500 conditions for each, or 11 pairs of blocks to stitch, 500 conditions. You don't want to do it by hand, okay? You want to do it under the guidance of some kind of an algorithm. So after the seeding, this was like the initial matrix of yield. This just gives you, like the initial set on which to start active learning. Then you vectorize it, right? And then you do something that is very familiar to you, I'm pretty sure. We take a new pair and new conditions from this space, and we try to choose the next move by the probability of improvement or to lower the uncertainty. And when the uncertainty is smaller or becomes smaller than the standard deviation over many trainings of our neural network, then it means we can say it's on the order of experimental error, and then we stop. And if not, we keep looping, taking new pairs and taking new conditions. And we go. Very, very simple. So this is how it worked. In the beginning, you see the model was predicting, this is like sorted conditions, it was predicting what is good and what is bad sort of randomly, okay? As time went on, meaning like our experiments went on, it learned how to predict high yielding and low yielding, and at the same time, its uncertainty of prediction dropped, okay? So it seems that the model actually learned which of these reaction conditions to apply. Now, this is very important. When it was learning, it was performing majority of reactions that failed. This is the blue distribution. This is contrasted here if we tried learning on the literature, what people publish, what I told you before. We would be looking only at examples of this type. But for learning, we need to know good and evil, right? So it went often into failed reactions, but it understood what constitutes success and what constitutes a failure. And then here's the important part. After it's trained, you take out of box, out of distribution, substrates, maximally different than what it saw during learning, and then you compare how well, what's the yield? Yield is like from 1 gram, if I can get 1 gram or 1 mole to 1 mole, it's 100% yield. That's good. If I get 0, that's bad. And this is what it predicts. Now, the important part here is that in all of these predictions, so it actually did quite well, somebody 15 years ago spent about 5 years with an entire group of people to optimize for this particular problem by hand. And their average yield was, what was it? I don't remember what it was, like 30% or like 25%. The yield this machine, this learning cycle did, ended up 72%, okay? So it's not perfect, but with 72% average yield for any kind of coupling, now you can use this reaction on the robot, and you can really use the robot in a robotic fashion, meaning without any supervision, any tweaking, and so on and so on. So that's good. Okay, and this was a science paper, which is also nice. So having done this, now you have a robot to rapidly make molecules, any molecules that you can imagine, because CC bonds are the core of organic chemistry. You can do it about 100 times faster than organic chemists. So let's apply this to solve some outstanding problem. And one of the problems was the so-called lasers, organic lasers, so functional materials. So this workshop is about materials and not molecules only. So we decided to use this iterative, you see, iterative, like one, on this machine to make the brightest lasing organic molecule in the world. This is a typical molecule of this type, developed by the Japanese in 2005. This has been the world record in terms of emission cross-section, how brightly it shines, okay? And you see it has a certain core, certain symmetric linkers, and caps here. So we took the blocks from all different catalogs that could serve as caps, about 40, bridges, about 68, and cores, 161, and we tried to make, under the guidance of an algorithm, we tried to make as many of these lasers and evolve them to beat the world record. So the space right now is much bigger. So 40 times 60, 2,400 times 160, it's about, I don't know, 410,000, something like that. Okay, so you got the gist, right? Now, every bond here, remember I told you the Suzuki coupling makes CC bonds between aromatic rings. And all of them are aromatic, so they're very well suited for the robot, okay? So here are some candidates. And of course, which candidates to make? Because if you calculate the space, I told you it's a couple 100,000. We cannot make them all still. So we need some kind of choosing, algorithm to choose. Here are some candidates. How do we choose? Well, it's again the familiar active learning, but this time we are going to be learning on the quantum properties, like emission cross-section, like some of the transition moments and all that stuff, quantum stuff. So, photoluminescence quantum yield and emission cross-section. This is the stuff after each round of synthesis. This goes to the neural network. It learns structure versus the properties that we observed, and we let it run in circles. Maybe I'll skip this. same kind of Gaussian process. And this is what it did. So initially, we did a little bit of tweaking with conditions, just a little bit. Then we explored more or less randomly, just to get enough knowledge to see the algorithm. And you see we're not breaking any world records. So this is how many of our new molecules were breaking the world record from 2023 or from 2025. And then the Bayesian optimization and active learning came last, okay? And as you see, we discovered on the order of 10 of these molecules that were actually the brightest organic lasers. To put it in the perspective, the Japanese group, there's an institute devoted to it, they managed to synthesize 12 such molecules in the last decade. And Japanese are not slow working. They're just somewhat hard molecules to make. Now, this entire thing took about 6 months from algorithm development to looping the synthesis. And some of these molecules, okay, you would say, this cap, it just borrowed from the world record. But look at in the middle, took something completely different. Or what it did here. I would never, as a chemist, I would have never thought about putting the cap this way and not this way. Why did it do it? I have no clue. Only AI knows. What is notable about this, and this is something, for this crowd, is all of this was happening asynchronously in 6 labs all over the world. So I was a, small cog in a bigger machine here because we collaborated with Alana Spuru-Guzik, no, here is Alan, Toronto, Jason Hine, British Columbia, Marty Burke. See, there is no United States. I thought that the United States is taking over Canada, but maybe Canada is taking over United States. Anyway, this is Illinois, okay? These are our labs in Korea and Poland, and Lee Cronin in the UK, okay? And all of this was happening. Data was coming from 6 labs, the algorithms were working, purchases were automated, and it worked like a dream. This is by far the biggest problem that I participated in the last few years. So, I still have a few minutes, right? Yeah, okay. Number 3, something different. So you might say, okay, fine, organic materials, yeah, you're making CC bonds because CC bonds are like easy to make or whatever. The Suzuki couplings, everybody knows about Suzuki couplings. So is this transferable to completely different, this active learning, can it do better in a completely different setting? How many of you heard about perovskites? Oh, material scientists, okay. So, perovskites are everywhere, from from photovoltaics to electroactive materials. So when my students first suggested that we get into this project, I was like, are you guys crazy? I mean, this is, this field is so populated that there's no way we're going to break any records because people have been working on this for decades, right? So there's no way. And they say, well, maybe we could, So what they wanted to do is to discover the best electrocatalyst for oxygen evolution reaction. Why? Because we're in Korea. This was done in my Korean labs. And in Korea, we need such materials for batteries and so on and so on. You heard about Hyundais and Kias and all that stuff, right? So, yeah. So the objective was, can we prepare a perovskite that is the best OER catalyst, electrocatalyst ever? And so here, I'll spend just 1 second on the vectorization, because we got, the graph neural network to describe the structure of the crystalline material, but then we built a surrogate model to actually predict X-ray, and we use this representation concatenated with the graph neural network describing the material, right? Why X-ray? Because X-ray is like a fingerprint of a solid state material. And in electrochemistry, you're trying to minimize over potential and minimize over potential and also uncertainty. This is the same active learning loop as we discussed before. So how many materials do you guess or guesstimate will it take to break a world record? How many of these perovskites should we make? Let's take an average. One. Okay. She's good. I will hire you. I was thinking few hundred. Okay. So what we did in the beginning is exactly the same playbook as before. You have all the possible perovskites composed of, there are two sides in perovskites A and B. So we took 5 metals and 5 metals. Okay. And we looked at this is the Tisney projection of the space and the same, 5, yeah. And the same playbook as before, take as randomly as possible. Yeah. So to be representative to the entire space. And the first round, we made 30. The model performance was, 0.88. That's not bad. And it was rivaling some of the best materials in the world, some of them. Yeah? But there were no clear winners yet. So we did okay just by sampling, but not quite. At this point, the neural network told us, yeah, but my predictions have very high uncertainty. So I'm making these predictions, but I really don't know what I'm doing. So, like we're not done yet. And you should probably consider looping back to minimize the uncertainty, which the computer did. And it suggested us 10 extra oxides. So first 30, state of the art, 10 more to make. At this point, I was like, damn, that's anti-learning. You see, they actually got worse, right? They got worse. So I'm like, nah, yeah, we're abandoning this project. However, remember what I showed you in the first of these looping things, that the computer likes to spend time in the failed reactions to learn what is really good. So I was a little bit more optimistic when I saw that at this point it said, look, but my uncertainty went down. Now I can make my predictions, okay? And it make predictions, including this material here. This is beautiful structural formula with over potential of 396, which is perceptibly less than the competition. Okay, we synthesized it. This is EDS mapping. So, elemental map, to make sure that everything is distributed uniformly. We predicted, or the model predicted the X-ray structure. We took X-ray, they matched like crazy. And here is the coolest stuff. It actually beats the world record by a lot this time. So this is the red one. 392 was the prediction, millivolts. And it gets you, 396, sorry. And 391 is the actual one. It has very low Tafel slope, which tells you about how the smaller the slope here, the better. So the red is good, and it's very stable. Okay? So this is a summary, how well it did compared to the competition. And we're almost done. The last stuff, so these three, tell me, at least me, I think it's safe to say, 5 years ago it was not safe to say, that these algorithms and robots are going to stay in chemistry. There's always this kind of flirt with the technology, and then it can be just abandoned. Hopefully, they'll stay. But we need to convince chemists, and I talk a lot to organic chemists, inorganic chemists, you cannot just publish papers on algorithms. They need to see the meat. They need to see, it solved the problem on which I was working for the last 15 years. Then we're talking, okay? It's essential that these technologies, algorithms and robots, that they enable discovery, not just, screening. Screening has been done in pharma industry for a long time. Really, discovery, okay? So, the reactions and networks in hyperspaces, I'll skip. This is slightly different. So if you're interested in what we're doing, This is our group side or the center side. I should say a few words about IBS. It's not irritable bowel syndrome. It's Institute for Basic Science, Korea, which has more money than Max Planck. Karsten should wake up. No. Right. Right. So it's a 10-year funding cycle, and you have to renew once. I can live with that. And this is my beautiful group, and of course, people are everything. Like you might wonder, why they dressed up like this. Retrosynthesis. Yeah, so retro is the Belle Epoque. So we went to a theater actually to take this picture, right? So let me just very briefly say that these beautiful ladies here. Sarah is the president of Alchemy. Eva is a director at Merck. Aga just goes to Lindau conference. The guys I will skip. They're very smart because they're Polish. That's obvious, right? And so this is my Polish group. I hold dictatorial power there because I have the golden hat. It's like the James Bond movie, Man with the Golden Gun or something. And professors I mentioned, Marty Burke, Alanas Puruguzik, and Jason Hein. This is the closed loop Suzuki stuff. And then my IBS group who build the robots, they're kids from all over the place, about, 12 countries by now, US, France, and so on and so on. So if you're curious about Korea, ask me about about this after the lecture. So that's what I prepared for you. Hopefully I did not antagonize you too much, but I wanted to maybe a little bit raise your blood pressure. So I'll be happy to answer your questions.
Thank you. It's always so lovely to see you present. I saw you present in Cambridge about a year ago, and it's once again wonderful work. Questions for Bartosz?
Hi, thank you for the great talk. Yeah, so as someone also who works with Bayesian optimization with also experimental data, it seems like your AI model is more well behaving than mine. You get some really nice results. So yeah, I would like to ask some more details on, you showed like a neural network looking model for your predictions and uncertainty. So could you elaborate what kind of a surrogate model did you use for the active learning part?
For which project?
For the, for the first one. So that was the synthesis.
No, it was very simple. For the Suzuki, I think we had, like a neural network, ensemble of neural networks with a Gaussian process kernel.
Okay, that's fine. And how about for the perovskites then? Is that also an ensemble neural network?
Very similar. So this almost became like a playbook for us.
Okay.
What was the model to reconstruct the X-ray? I think it was a transformer model.
Okay, that's fine. But then, because neural networks need quite a bit of data, do you remember, like in the end, how many like samples did you make to get the like world record results? Like is it hundreds or?
For the lasers, we did about 500 syntheses, right? We attempted, out of which 350 worked, right? Because it's when we say we did synthesis, like stitching 5 blocks together, right? So the chance of every individual stitching working is like 80-something%. So when you multiply this, it gives you maybe like 75% success rate. So 500, 350, yeah, so this was roughly it. For the perovskites altogether, we made 40, but I strongly suspect that this space, I haven't seen it, for the photovoltaics, but I suspect that the space is not extremely corrugated. I think that the space is more like that. And here we were a little bit lucky, okay? In the first project, we did the space, the first project about 200, 220
Okay.
or something.
Okay, yeah, thank you very much.
Thank you very much for this brief run through. It's amazing that these things really do work in practice and they're here to stay and we can use them. Now I want to stir the pot. Is it time to put the human into the loop? How is your feeling on this?
see the first part of the talk where I was telling you about this design of synthesis of organic molecules without human in the loop there, teaching the machines, like AI is completely powerless. It's just a different problem. Like where we started, right? When I said that here is a problem in which I found AI pretty much useless, right? It was an expert system in the end. It was a little bit of a mixture of AI. The three that I showed you, I'm still debating it. Is it, maybe we're incredibly lucky or something. I'm sure there are problems in which you do active learning and you do 1,000 experiments and you're just being frustrated. Let me give you one example, drug discovery. How many drugs AI discovered so far? 0, right? If you read Derek Love's blog, he has like every 3 months, he sort of vents on AI and cheers whenever like AI company goes bust, right? I know why he's doing it, because he's a medicinal chemist, so very practical person, and he probably hates these bombastic claims that, like, who was this? Hassabis recently went on 60 Minutes and said that in 5 to 10 years we'll eradicate disease, not just cancer, any disease. Why? Because isomorphic is doing what? Docking? I mean, I'm sorry, that's a heresy, right? We shouldn't be over optimistic. So in cases like medicinal chemistry, drug discovery, the space of molecules is just so huge. And then it's not only the molecule that needs to bind to some protein, like to predict binding, like, what AlphaFold was trying to do, but you need to also understand toxicity. You need to understand off-target binding. You need to understand hERG, so cardiotoxicity, and so on and so on. So we have decades, if not centuries, before any of this will materialize. And I actually do not know whether AI is the way to go. Daphne Koller from Revolution Medicine. Revolution Medicine is a company that is worth right now about $5 billion. And Daphne used to be a Stanford professor. And she says that in medicinal chemistry, in drug discovery, it's not a problem of AI. It's a problem of data. Had we had 5 million high quality data points, maybe we can talk. But like we're having like few thousands here, there, companies don't share, and so on and so on. So coming back to the question, there are problems maybe in material science where you have well-defined, crystal structure, where you have one property that you're trying to optimize, maybe electroactivity, electrocatalytic activity, right? Maybe AI is great, and commensurate with our ability to produce data, maybe on the robots. But in this kind of molecular sciences in general, I am much less optimistic.
I think that we're going to have to pause it there. The coffee is outside, but remember, Bartosz will be part of the panel discussion. You can all